Howdy folks. So today what I'd like to do is go over the idea of the derivative of exponential and logarithmic functions. So to start off, we're just going to say what's the derivative of b to the x? B to the x being any exponential function base b. So we don't have any tools to do that using calculus right now. So what we're going to need to do is develop some tools by going back to the definition of a derivative. So in this case, if I say that the derivative of b to the x is equal to the limit as h approaches 0 of b to the x plus h minus b to the x all over h, that would be our definition of a derivative. Now, just to bring attention to it, the argument is in the exponent position in this question. So the b to the x, if we go to f of x plus h minus f of x all over h, in this case, the x plus h all goes into that same argument position in the exponent. So that's why it's up there like that. There's not a whole lot we can do to switch things around, but we can do one little thing. We are usually doing this in reverse most of the time, but we can split this up into two exponential pieces for that first term. So b to the x, b to the h. You would be most likely, you'd find it easier to recognize going in reverse. So if you have b to the x, b to the h, you'd say, oh, they have a common base, so therefore I can add the exponents, which would become b to the x plus h. So in reverse, b to the x plus h can become b to the x, b to the h, which that's what I did. Once we've done that, we actually have a common, so if I just kind of show you here, that's b to the x in both of those terms. So what we can do is take that b to the x and bring it right out to the front because it has no h in it, so it can go right through the limit as well. So if I do that, we're going to come up with b to the x, and then the limit as h approaches 0 of b to the h minus 1 all over h. All right, so b to the x, that's kind of its own thing. That's fine. What we're left with is something a little bit peculiar and interesting, and that's what we're going to spend a little bit of time exploring, is this limit as h approaches 0 of b to the h minus 1 over h. On first glance, if we just chuck a 0 into it to see what the behavior is like, b to the 0 is 1, so we get 1 minus 1 is 0 in the numerator, and in the denominator we also get a 0. So this is an indeterminate form, and it's not one that we should be comfortable with at this point. So if we feel we're not sure exactly how this behaves, that's entirely reasonable. So we're just gonna, I'm gonna advance my slide here and show you a little something that I kind of prepared in advance. So this is the idea that the limit as h approaches 0 of b to the x minus 1 over h. That's what we're looking to describe. I'm just going to take two random b values and see what happens. So I picked 2 and 3. And some of you, if you have really good number sense and have played around with some funny numbers before, you might actually recognize what those two values are. If you don't, that's pretty reasonable. So it's don't worry too much about it. But if you don't, then these are two very random numbers. However, they don't appear to be approaching 0, for instance. The rate at which this is approaching 0 is slowing down so much that doesn't seem very reasonable. It instead seems to be kind of honing in on something like 0.6931 blah blah blah. Okay, well, that's great. And over here we get this 1.0986 blah blah blah, and we might see that it drops a little more or whatever, but they seem to be at least agreeing on the first few digits after the decimal place, after we've gone and taken an h that's even just not super small, but you know, the thousandths, the 10,000ths, the 100,000ths, and we see that it appears to be converging, although we may not know how to describe that number to which it actually is converging. So that's interesting enough. But let's just say, for argument's sake, that there is some value that is in between 0.693 and 1.098, blah, blah, blah. That is nice. What might that number be? Well, how about the number 1? So if we actually say, let's say that the number 1 is somewhere in between those two. What's a number between 2 and 3 that we could try? Well, we might even define a number between 2 and 3 that gives us 1. That could be one way of looking at this. But we could also take this constant e that people have already come up with, and we could work with it and see what happens when we take e to the h minus 1 over h. And if we do that and we take it to that same 100,000th place, it really looks like this is converging to the number 1, which is kind of exciting. You can go through and do something that's a little more formal of a proof when it comes to showing that the derivative of e to the x is what it's going to become in just a moment. But for the time being, if we kind of focus back on the last thing that I had covered on my iPad screen, which is this thing right here, what would happen to this if the original function was actually the derivative of e to the x, where e is not any base, e is the specific base that goes along with the number 2.718 blah blah blah. So if you are that value, which is an irrational number, which we call e, that's the number that I'm using right here. So the derivative, according to this, would be equal to e to the x, the limit as h approaches 0 of e to the h minus 1 over h. But that thing is what we just talked about on the screen where I have all the numbers. So right over here, we would have those values approaching 1. So e to the h minus 1 over h, as h gets really, really small, appears to approach a value of 1. So what we can do then is say that the derivative of e to the x is equal to e to the x. Really nice derivative, and kind of appropriate, I guess, in a land and time where we're talking a lot about exponential growth, that you see what exponential growth really means. Exponential growth is growth where the speed of growth is proportional to the amount of stuff that you have in the beginning. So if you say y is equal to e to the x, that means that you have an exponential function, but if you just want to evaluate it at any particular time, you put in an x value. But the speed that it grows is also e to the x. So not just proportional in this case, it's actually equal. If we look at other exponential functions, we go back to the b idea, then we could see that we're talking about proportional, but the derivative of e to the x is actually e to the x. So the rate of change is equal to the y value, which is pretty cool. So that's going to be one of the important things that we come up with today. We're going to extend that a little bit in a moment. First, I'll just take a couple examples of derivatives that involve e to the x. One of my favorite things is that it's really simple in terms of a derivative. So e to the x is e to the x, and so when we incorporate it into other things that we know how to do, it's usually pretty straightforward. So we'd have y is equal to x e to the x, which means that y prime is equal to, this is going to be a product rule, so we have x times e to the x. If I take the derivative of x, it's 1, and then I would just be left with the other thing left alone, so e to the x plus x, and then the derivative of e to the x is e to the x, so even though it looks like I didn't do anything, I actually did, and so we would get, in this case, e to the x plus x e to the x. If we wanted to, we could factor out the e to the x and get e to the x times 1 plus x. It's pretty tidy. Next up, if we do the second one that's written there, y is equal to e to the cosine x. So we'll put a trig function into the argument position on that particular exponential. So we'll have y prime is equal to, and this is going to be a chain rule. So the derivative of the outside is the derivative of the exponential function e to the x, which is e to the x. So we take that derivative, leave the inside alone, times the derivative of the inside function. The derivative of cosine is negative sine x, and so we're done there. You can put negative sine x e to the cos x if you want to, but it doesn't really need to be tidied up. All right, so another example, just in this case, we're going to use implicit while doing this. So I'll start out by just saying that e to the y is equal to x minus y. So if we do implicit differentiation here, because if we try to get y isolated first, in order to get it out of the exponential function, we're going to have to take a natural log. In taking the natural log, we'll be able to bring the y down, but then we'll trap the y that's on the right-hand side of the equation inside of a logarithm. And we'll be basically stuck in the same sort of position where you have a y inside of a function. You'd have to do the inverse to get it out, but then you trap the other one inside again. So instead of getting into that loop, we are going to do this implicitly. So we treat y as a function of x, and see where that goes. So we'll take the x derivative of both sides, e to the y, leave the inside alone, times the derivative of the inside, which is going to be y prime. On the other side, the x derivative of x is 1, and the y derivative of y is y prime. Or sorry, the x derivative of y is y prime. Now we have the y prime in two different positions. So I'm going to get e to the y, y prime, plus y prime is equal to 1. Factor out the y prime and get e to the y plus 1 is equal to 1. And finally, y prime is equal to 1 divided by e to the y plus 1. All right, so again, just being able to use the e to the x derivative being e to the x inside of an implicit case. All right, so switched up the letter for some reason. So in this case, I have y is equal to a to the x instead of b to the x. But we're going to go back to the original problem that we were posing because I got sidetracked and basically did the derivative of just the e to the x function instead of the original any base. So back to the any base example, we would have y is equal to a to the x. So let's take the natural logarithm of both sides of this particular equation. And so I'm going to do the natural logarithm of y is equal to the natural logarithm of a to the x. The reason I'm going to do this is because I might just not really appreciate that x, I guess, where it is, especially because I don't know what to do with it now that I have this a involved. So that's going to give me ln y is equal to, and then it's going to be x ln a, and then I'm going to put that back up and say e to the power of, so I'll write that in a different color just so you can see what I'm doing. E to the power of that stuff is equal to e to the power of that stuff. So we'll get our y back, and it's going to give me e to the x ln a. Now, there's a kind of a faster way that I could have maybe done that from the original statement, but I find that this method gives you a little bit of an easier path to follow along. So we get y is equal to e to the x ln a. Now, in this case, this is now something I can handle because the function that y is equal to is an exponential function base e instead of an exponential function base a. So if I'm looking to describe the derivative here, the derivative of e to the x is just e to the x. But the inside is a function, so I have to apply the chain rule. So it is now multiplied by the derivative of the inside. Ln a is actually a constant. That is not a logarithm of some changing value. It is the logarithm of the constant a, natural logarithm. So that's just a number. And so we can think of it as just a constant multiplied by x. And so the derivative of constant times x is just that constant. And so written out beside my exponential piece there is the chain rule derivative of the inside, which just gives us the constant ln a. So if I want to kind of tidy this up a little bit, we could say that the derivative is equal to, now I'm just going to change the order that things are written up there. So it's going to be ln a, and I'm going to, ln a times x, and then we're going to, oh no, actually, do you know what? I'm going to change my mind on the way that I'm doing that right there. So I'm going to use an exponent law and take the ln a to the power of x. So I took this little x that was on the front, and I'm going to basically pop it up as an exponent because a coefficient on the front of a logarithm can be equal to the power of the argument inside of the logarithm. So I'm going to do that. I still have my ln a kicking around at the end. And so if I take the fact that e and ln are inverse functions, then we can basically have that part cancel and leave us with just the argument inside, which is a to the x, and then I have ln a. And so this actually is the derivative. So if I have y is equal to a to the x, the result of that is a to the x ln a. So it kicks out an extra constant. E to the x doesn't kick out a constant. If you use the, well, it kicks out a constant of 1. If you use the same rule, then it would be e to the x ln e, but ln e actually is 1. So it would work out the same way. And so now we've actually shown what the derivative of every single exponential function of various bases are. Of course, you're not doing anything with like bases that are negative or things like that. But when we described exponential functions, we were not interested in those bases anyway because they wouldn't behave well at all kinds of numbers. All right, so we are going to take a deep breath and then approach the inverse function, which is the logarithm. Now, if you, through the magic of video and the internet, if you want to pause right now and think to yourself, how would I attack this problem so that I don't have to go back and use definition of a derivative? Because if we can avoid doing that, then that's a really, really good idea. So unpause, and we'll see that if we were to take this and say, that is an inverse. What did we do with inverses last time? So our trig functions, inverse trig functions, when we developed those, we wrote them by taking the inverse of what was going on right away. So I'm going to write this particular thing down. Y is equal to ln x. And then I'm going to do the inverse of the natural logarithm, which is the exponential function. So I'm going to put e to the y is equal to e to the ln x. The purpose of that, of course, is to get the x down out of the variable position, or sorry, the exponent position. It's in a nice spot now. And the function that I'm left with, I know how to take the derivative of that now. So that's an e to the x function, except for the argument this time is a y. So that's going to be done implicitly. So e, leave the inside alone, times the derivative of the inside, which is y prime, is equal to the x derivative of x, which is 1. And so if we shuffle things around, we're going to have that y prime is equal to 1 over e to the y. So in this case, I can backtrack a little bit and say, ooh, but e to the y, I have a statement for that right here. E to the y is actually just x. So we can tidy that up even more and say that y prime is equal to 1 over x. That's actually really cool that can be equal to just 1 over x. So if I leave it at that, what we've said is that if y is equal to the natural log of x, y prime is equal to 1 over x. That's a pretty tidy derivative too. Didn't have to go to definition of a derivative, thankful for that, and it wasn't too bad as long as you're comfortable with following along with the implicit differentiation. All right, so we want to expand that into what would go on instead if we were to have any old base. So in this case, I put the base as being a. And so we're told that y is equal to log base A of x. All right, so I am going to do a change of base formula here. So that might be something that is a little bit rusty from Pre-Cal A. So that was a long time ago for most of you. And if we apply that here, then I can rewrite this as the natural log of x divided by the natural log of A. So I've changed the base here from an A to an E, which is what the base is on a natural logarithm. But if you remember kind of what goes on there, this value x goes inside in the new base in the numerator, and this one here goes inside of the new base in the denominator. So log base A of x is the same thing as ln x divided by ln A. Now, I'm going to attempt with this new form to do the derivative of this function. It screams quotient rule, especially since you see the logarithm in the denominator and you say, oh, it's a function. Logarithms are functions, but it's acting on a constant, so it's just a constant value. That's the same thing as 1 over ln A, which is just a constant, times ln x. I would be much more willing myself to try to attack it that way rather than to mix in quotient rules in an unnecessary way. So that's before we get going there. That is not the derivative. That is actually the original function that I've just changed the look of. Now I'll take the derivative. So in this case, y prime is equal to constant multiple rule, so I just leave this out front, times the derivative of ln x, which we just came up with. The derivative of ln x is 1 over x. So I come down here and I say that that thing's derivative is 1 over x. So now we have that the derivative is equal to 1 over x times ln A. We'll just multiply our two denominators together. Not for any good reason, but I'm going to put the x out front just because it looks a little tidier. We can separate the x and the a that way. And so we have our end result that if y is equal to log base A of x, then y prime is equal to 1 over x ln A. So that is the result of the logarithm of any base. All right, folks, so I had made a bit of a faux pas in that I went ahead and did the next part that I'm going to do with you after this, which is the derivation of the power rule for all real numbers. But one of the problems was I actually did not do this first, which is going to allow me to use negative bases. Technically, I did the right thing for showing real numbers, but I gave no reason to believe it would work for bases that are not positive values, because the logarithm function, the way that we have it, needs an argument that's positive. Now, this particular version of the logarithm function takes anything that's negative and turns it into a positive first. Now, that might seem kind of hokey, is the way that I would describe that. Okay, well, if you're just going to turn it into a positive number anyway, well, what's the real interest in doing that? Well, the real interest in doing that is because the derivative ends up being the same, whether you're actually using the ln of x or the ln of the absolute value of x. Because that's true, you can actually use the ln of the absolute value in place of just the ln of x anytime that you want. Let's actually show that that's true. So if we were to describe the ln of x, the ln of the absolute value of x as a piecewise function, we would have to break it up into what happens when this thing's positive. And if the x value, if the argument is positive, nothing happens to it. The ln says, great, it's going to be a positive value, that's going to be fine. The absolute value says, there's nothing I got to do because it's already positive. So we would just take the ln of x, and that happens anytime we have a positive value for the argument, so when your x is greater than 0. If your x instead was going to be less than 0, that's where something weird has to happen. So the absolute value is going to receive a negative number, and it's going to say, nope, I'm going to change that back to a positive. So the way that we show that happening is you're going to get the opposite sign of what's going on there. So you're going to get a negative negative. Then the logarithm's going to apply on it. So we have the logarithm of the negative value that's been turned into a positive, and that happens when your x is less than 0. When your x is equal to 0, it doesn't really matter. Your logarithm is going to be broken. There's no positive, negative, 0 kind of thing to fix or worry about. It just doesn't work. And so I'm not going to use any part of my piecewise function to show what happens at a value of 0. All right, so now if we wanted to show what is the derivative then of the ln of the absolute value of x, we are going to show that by taking the derivative of the first part of our piecewise and the second part of our piecewise. So the derivative of the first part of our piecewise here is actually going to be the 1 over x, because we've already shown that that's the case. So the derivative of ln x is 1 over x. The derivative of ln of negative x is a small chain rule. So it's going to be 1 over negative x times the derivative of the inside, which is negative 1. That's a great result because what that does for us is it shows that by simplifying that bottom part, it also gives us 1 over x, negative times a negative. So as a result, we actually get that the ln of the absolute value of x, like this, its derivative is also just 1 over x for all of its domain. That is actually going to be helpful for what we're going to do next. So, and now back to actually showing properly that the derivative for the power rule works for all real numbers. So, when we start this out, y is equal to x to the power of n. That's true, which means that if I somewhat randomly put an absolute value on both sides of that equation, if a negative is equal to a negative, then taking the absolute value of it is going to be okay. Positive equal to a positive, taking the absolute value of it is going to be okay. It's more restrictive to not have the absolute value there, but I'm going to add them in. I'm also going to take the natural logarithm of both sides of my equation, like this, and then I'm going to also write the right-hand side of that a little bit differently. So this one I'll talk about a little bit more. So if I have the logarithm of the absolute value of x to the n, that means I'm taking some base and applying an exponent on it first, and then doing the absolute value. If x to the n is a positive number, then the absolute value will do nothing afterwards. If x to the n is a negative number, then the absolute value will turn it back into a positive, and I'll get a positive result. On my next line, I instead have a x inside of an absolute value. So if the x is positive, then it remains positive. If the x is negative, it remains negative. Or sorry, it becomes positive. And then I'm going to apply the power on it afterwards. Since the x has been turned into a positive before the power is applied, the result has to be positive in both cases. Just like the result has to be positive in both cases if you take the absolute value after the power has been taken. So in both of these cases, we're going to get something that is always positive. And since it's always positive, and it's basically the same value, x to the n, those are actually equivalent expressions. That's going to be important to me because I'm going to take this exponent now, and because it's an exponent on something that's inside of a logarithm, it's an exponent on an argument inside of a logarithm, I can take that and pop it down to the very front instead. So I'm going to rewrite this as the ln of the absolute value of y is equal to n times the ln of the absolute value of x. So next up, I know how to take the derivative of everything that's written down there, because the derivative of a logarithm of an absolute value is what we just went through. Now, in the first case, I want to take the x derivative of everything, and the x derivative of y is going to be an implicit differentiation. We're going to use chain rule there. So we would have 1 over y, because the logarithm of an absolute value of something is just 1 over that something, times the derivative of the inside. The inside is actually the y function, because you can think of it as it's the logarithm of an absolute value of something. It's like logarithm absolute value is your outer piece, and your inner piece is the y. So it's y prime is equal to, constant multiple rule just leaves us with the n there, times the derivative of the ln of the absolute value of something. In this case, it's just x derivative, so it gives us 1 over x in the end. Now, we can say then that the y prime is equal to n, multiply the y up onto the other side, divided by x, which gives us in the end n, and our y is actually, if we teeter all the way up here, y is equal to x to the n. So I can write that instead as x to the n all over x. So we have a division of two bases that are the same. The denominator is basically an x to the 1. So we can say that this is n x to the n minus 1. And that should look really familiar because that's the power rule. And now that's properly done for the for all real numbers, including if the x value is negative. So one of the problems was when I first did this is up at the very beginning, if you just treat this like I did, but instead of having the absolute values, you don't include those, then what happens is you get to the same result in the end, but that doesn't allow for x's to be negative, because as soon as I place the logarithm in this line right here on both sides of the equation, it ends up giving you an issue where the domain of both sides can only be positive values that you're putting in there. Now with the absolute value, those can be positive or negative, just not 0. And so this shows you that this is true as long as the x value is not 0. But if the x value is 0, why are you caring about power rule? So we're good. All right, now let's just take a couple little things to finish off. Just play around with the derivative of logarithms. So in this case, if I have y is equal to the natural log of the tan of x, again, we could put the absolute value, but I'm probably not going to just throw it around everywhere, only when we really need to. Otherwise, I'll only care about this when it has a positive argument, and we'll just assume that that's the case unless we're told really explicitly otherwise. So y prime is equal to, derivative of the outside would be 1 over the inside left alone times the derivative of the inside, which is secant squared x. Again, we might be able to tidy that up a little bit. I'm just going to leave it the way that it is. Next up, I'm going to say if y is equal to the natural logarithm of x squared minus 3x all over e to the x cubed. So this one is everything's involved in the quotient. So we'll start off by doing quotient rule. Y prime is equal to low d high. And so d high is going to be 1 over the argument left alone times the derivative of the inside, which is 2x minus 3, minus high, d low, and this is an exponential function. And so derivative of e to the x is e to the x, so it's just e to the inside left alone times the derivative of the inside, which is 3x squared, all over the bottom squared. And so the bottom squared in this case is e to the x cubed all squared. We could multiply the exponent in and just get e to the 2x cubed. I think I said x squared the first time. That's e to the x cubed all squared, and it would be e to the 2x cubed. Sorry about that. So yeah, this part here should be all on one line. It kind of is, but it's a bit of a mess there. And so there, that's another example of just doing some derivatives involving the more clutter, more mess there. But now what you really should do is just take the time to try out some problems that have both exponential and logarithmic derivatives in them. And we'll go from there. Thanks.